Hello everybody. Today I want to present you the program asxp, the Algebraic Surface Explorer. This is the main screen. The program deals with surfaces in three-dimensional space with coordinates x, y, z that are given as vanishing sets of a polynomial in x, y, z and two parameters a and b. It can produce various perspective views of such a surface. It can triangulate them and display perspective views of the triangulated surface. It can apply certain algorithms on the triangulation to smoothen it out or reduce the number of triangles. And finally, it can generate data from the triangulation, which can be used as input for a 3D printer and so produce a physical 3D model of the surface for two given values of the parameters a and b. The equations which shall be used are contained in the file asxp.conf that is read in at the start of the program. In asxp.conf, every equation is associated with a name, and it is the name which is selected in asxp for further processing. Additionally, one can select one of three surface types: manifold, manifold with boundary, and non-manifold, which is necessary for surfaces having only one side or consisting of several irreducible components. So let's take a look at the configuration file asxp.conf for a short digression. So this is a configuration file, and here, for example, we see an equation containing parameters a and b and variables x, y, z, and defining a quartic surface in 3 dimensions. Below are other surfaces which we can view with asxp. First, let us now create some perspective views in one of the three main modes of view which asxp provides, namely silhouette, colors, and dots. Silhouette we take first. Silhouette, as can be expected, produces a silhouette view of the surface. Colors produces a colored view with a simple lighting model of parallel light falling from the direction of the viewer on the surface. Dots produces a Floyd-Steinberg-dithered rendering of the lighting calculated in colors. It is intended for the production of black and white illustrations. The perspective model used for these renderings is parallel projection along the z-axis. The viewer is, so to say, at infinity with a coordinate origin projected onto the mid of the screen and a horizontal x and a vertical y-axis. The surface is cut with a sphere of radius 8, centered at the origin before display, which is necessary as many algebraic surfaces have unbounded extent in real 3 space and only the inside of the sphere is displayed. The parameters a and b in the determining polynomial are set by moving with the mouse over the display window. They are derived from the x and y position of the mouse by linear transformation. From this model, it follows that if you want a neighborhood of a point P in surface F to be displayed, you have to give an equation for F so that P is the coordinate origin. This is not optimal but works quite well if you prepare the equations with a computer algebra system anyhow. In the next version of the program, it might be possible to specify the center of view point in 3D space. We can turn and tilt the surface by using the sliders called Euler winkel. They control the Euler angles by which the surface is turned for the perspective view. So we do not change the point from which the view is taken, but turn the surface around the origin in coordinate space. The silhouette view is the basis of a more refined version of display, which is intended for black and white illustrations in books and papers that shall convey an especially good impression how the surface bends and twists in 3D space without resorting to a lighting model and a photorealistic rendering. The means to achieve this is to calculate the principal curvature direction cross field. That is, for every point on the surface, the two directions in the tangent space are calculated, where sectional curvature is minimal or maximal. To put it in another terms, two eigenspaces of the Weingarten endomorphism are determined for every point on the surface that corresponds to a displayed pixel. In a second step, two systems of curves on the surface are produced, which are tangent either to the maximal or to the minimal curvature eigenspaces. These lines are then shown superimposed on the silhouette image of the surface. This gives a vivid description of the way the surface is situated in space, and even can give a hint that the surface belongs to a certain special class of surfaces, for example torsal surfaces, where one of these families of lines are straight line segments. As already seen, we have four control elements that influence the way this view with curvature lines is produced. First, to activate it, coming from the silhouette view, we have to check the checkbox Display Flow Lines. Then with the checkbox Display Cross Field, we control the display of an indication of the curvature cross field directions. These crosses here. Take them away or get them. Typically we don't want or need these, only the flow lines are displayed. With the button Reset Flow Streams, we start a fresh calculation and display of the flow lines. The select box below Reset Flow Streams, containing the choices Jobard and Mebaki, gives us the choice between two algorithms for placing the flow lines in the image. Both are named after the main researcher who described or implemented the corresponding algorithm. Mebaki is newer, faster, and usually of better image quality, but the older Jobard is also viable, albeit it takes in most cases a remarkably longer time to finish. So let's calculate this with the Mebaki method. So here we have the flow lines. Now go to the another surface, for example a quadric. Calculate the flow lines. Now we have here an ellipsoid. And we calculate again the flow lines. They are typical for an ellipsoid with these kind of points here. So we go back to the original quartic surface. We turn and tilt it. Now we calculate again the flow lines. Okay, so let's do something else, namely we want to triangulate the surface. We go back here to the color display first. And by clicking on the triangle system symbol in the toolbar, we can triangulate the surface. This gives us the opportunity to render it through the OpenGL library, which provides more possibilities for shading, illumination, color, and viewing perspective than is realized by the primary rendering engine of asxp, which is optimized for speed calculation of the surface changing under variation of its parameters a and b, and for calculation of the before mentioned cross-field streamlines. So we have clicked on the triangle system, and the progress bar below has shown us that all the steps necessary for the calculation of the triangulation are done. And a view here on the text console, we get some information about the process. 86,364 triangles or faces are processed, and the final number of triangles are 43,684. So now we go back to the program asxp, and now we go take a look at our triangulated surface by selecting the viewing window named AltGL, which means Alternative OpenGL Viewing Window. We can also turn the surface with sliders, but currently not in the same way as is possible for the main viewing window. We only have 2 dimensions of freedom to choose. So this does not work. These 2 here are working. If we take a closer look at the surface, we see a certain bumpiness. Especially here it can be seen a certain bumpiness, which is an artifact of the triangulation process used. A library from the comprehensive computational geometry package cgal does the main work. To reduce the bumpiness, we select from the select box named Taubin steps a value different from 0, for example 30. The number chosen gives the number of times a so-called Laplacian smoothing is applied. This kind of smoothing was first described by Gabriel Torbin in an IBM research report and as having the much sought after property of not shrinking the triangulation net after its application. By again clicking the triangle symbol, a new triangulation is started, which is now followed by 30 times application of Tobin smoothing. It takes some time, so we have to be patient and can take a look at the debugging output to watch the progress here. Now here we have 100% done in the progress bar. And if we now take a look at the window, we see the surface is totally smooth, no sign of bumpiness or so left. So next to another possibility of the program, reducing the triangulation. Triangulation is done not only for display purposes, it is also the preliminary stage necessary for generating a 3D model of the surface suitable for 3D printing. For this goal, it is desirable not to have too many triangles in the triangulation because there are limits on the file size and number of triangles for model files for 3D printing, for example, the popular STL file type. So we have the possibility to reduce the number of triangles by clicking on the respective button in the toolbar. The amount of reduction is chosen by the spin box tree reduction percentage, which contains the percentage of triangles remaining after the reduction is done. The default value 40 is a reasonable choice, as bigger reductions incur the risk of introducing unwanted artifacts into the reduced triangulation. But in the end, there is no problem in finding the optimal value by trial and error. So let's do the reduction here. We look at the console, there's some output, so the reduction is already done. And we can now view the surface here with an RGL with a reduced number of triangles. It also looks quite well. Also, although it has 60% of its triangles lost, it still looks quite smooth. After a triangulation has been produced and optionally reduced, we can produce a pre-print stage file, which is intended to be converted into a real STL file suitable for 3D printer control by a special command line utility called render-stl that augments the program asxp for this kind of application. To generate this pre-print stage file, we press the button with the ascat icon on the toolbar and generate a file model.ascat, which is the input file for render-stl and which generates the full-blown model.stl through which a 3D printer can be controlled. So here we see, and OpenASCAT is set as a program, the production of the model file model.ascat has been done. So a preliminary file with a file size of about 12 megabytes has been produced. Now a last remark on 3D printing. Of course, the triangulated surface needs to be augmented with the thickness parameter to give a spatial model with non-zero volume, which is needed for 3D printing. This thickness is given by the spin box shell thickness. Its value is in the same units as a radius of 8 units, which is the radius of the ball that the surface is intersected with. So if you think of the surface intersected with a ball of radius 8 centimeters, then the default thickness is 0.2 centimeters, that is 2 millimeters. So now most or nearly every function of the program has been explained. Now we take a look at some surface here that are available we haven't looked at before. For example, the Clebsch surface here, and we view it from several sides. We turn and tilt it. In fact, for every frame that is displayed here, every pixel of the viewing area here has been calculated. So it's an 800 by 800 viewing area, and all 640,000 pixels must be calculated in every frame, which is done with the help of CUDA graphics card calculation accelerator. Now take a look at this. Here we have a variety that has two components, a sphere and a plane. Now we take a look at Bart's sextic. Here we go to the silhouette view. And again calculate the flow lines. Or as an alternative, we go to the Floyd-Steinberg desired rendering. Take cylinder and again go to the silhouette view, display flow lines. Now we see one system of flow lines are straight lines, parallel straight lines, of course, as expected. And finally I end the program, and this yes, this was a demonstration of the program up to now. Goodbye.